So welcome to Everyday Mathematics. Now today we move from problem 34 to problem 35 of the 2024 Caltech Math Mid Final. Now the problem in question is the integral from x equals to 0 to x to infinity of the fractional part of x raised to the ceiling of x over 1 plus the ceiling of x. So let's see how we may be able to solve this problem. It's certainly a very interesting one. A couple of things that need to be noted is that the fractional part here of of x is the difference between x and the integer right below it. That means that is x minus the floor of x. So with that in mind, let's now go ahead and try and solve this problem. So for this problem, we now understand what this fractional part of x means, designated by the curly brackets around x. So since x is the fractional part of x is x minus the floor of x, that now means that our problem now can be re-expressed as being equal to the x minus the floor of x raised to the ceiling of x over 1 plus the ceiling of x. So something notable here is that the ceiling of x, it means it's the integer right above x in the event that x lies between k and k plus 1. So the ceiling of x is going to be equal to k plus 1, and we say that that is when x is greater than k but less or equal to k plus 1. The floor of x means it's equal to k when x is greater or equal to k or less than k plus 1. Therefore, our fractional part of x is just going to be equal to x minus k in the interval x is greater or equal to k and less than k plus 1. Therefore, now our problem now can be expressed as follows. We will have to discretize our integral into steps of k, and so within each step we're just going to have to integrate the value between each step and then summing up all the steps. So between k and k plus 1, our integral is x minus k to the power k plus 1 over 1 plus k plus 1, which is x minus k to the power k plus 1 over k plus 2, integrated from k to k plus 1. And then we sum it up from k equals to 0 to k tending to infinity. So what is notable here is that the integral here becomes x minus k to the power k plus 2 over k plus 2 squared, and now we have to apply the limits appropriately. This all summed from k equals to 0 to k tending to infinity. So with that in mind, what happens is that we can now substitute in our limits when kx is equals to k plus 1, that is k plus 1 minus k raised to the power k plus 2 over k plus 2 squared. So this k is cancelled, so we have 1 over k plus 2. And then when x equals to k, we have k minus k on the lower limit. This is 0. So we are left with the summation from the summation of 1 over k plus 2 squared from k equals to 0 to k tending to infinity. Expressing this in a more expanded form, when k equals to 0, we have 1 over 2 squared. When k equals to 1, we have 1 over 3 squared. When k equals to 2 is 1 over 4 squared, and so on, all the way to infinity. But we know of the Basel problem, which tells us that when you're summing 1 over k squared from k equals to 1 to infinity, that is equals to pi squared over 6. If you don't know much about this, I welcome you to search for it. Go online and you will see the derivation. But then what this means is that our problem here is the same as the Basel problem minus 1 over 1 squared, because the 1 over 1 squared and this one would cancel, but we want to express it this way so that now we can substitute pi squared over 6 in place of this minus 1 over 1 squared, which is 1. So re-expressing things here, we have pi squared over 6 minus 1 as our answer. So what that means is that our integral of the fractional part of x raised to the ceiling of x over 1 plus the ceiling of x from x equals to 0 to x tending to infinity is pi squared over 6 minus 1. And that is the answer that was expected. Now, we hope you really enjoyed following along. If you haven't subscribed to our channel, we do really encourage you to subscribe to our channel. If you like what you see, please share. But until next time, have a very great day ahead. Thank you.